Well, good morning, everybody. Welcome to Ellensburg, Washington, USA. The time is 8:47 in the morning, and we will begin our program on paleomagnetism at the top of the hour at 9 o'clock local time, about 12 minutes from now. So if you're watching this in replay form, go ahead, skip ahead 12 minutes and we'll begin the program. But we always start a little bit early with the early arrivals. Wow, we already have 235 people hanging out. Great. How's everybody doing this morning? I'd love to say hi to some folks. Hello, Finland. Great to see you. Evelyn, age 8. Uh-oh. Have I been saying your name wrong, Evelyn, or did you just have a birthday? If you did, happy birthday, Evelyn. I always say Patrick age, I'm probably off on your ages a little bit. Dale, Big Dale, Illinois, South Carolina, Martin from the Netherlands, Red Deer, Alberta, Heinrich from sunny Denmark. That sounds delightful. Wish I could be over there. Puyallup, Belgium, good morning. Thousand Oaks, California, Mercer Island, that's near Seattle, in the greater Seattle area, shall we say. Chris is from Seattle. Laramie, Wyoming. Chicagoland 5x5. WLS Chicago. Had my little AM radio back in the 70s. How'd that go? Don't be nervous. Don't be rocky. Here's a teenage. Get the jockey now. WLS Chicago, Newport, Oregon, Bellingham, home of Merle Beck. I'm not sure if he's still in Bellingham, but he was for much of his career. We'll be talking about Merle this morning. Springfield, Ohio. It's terrific to have you all with us. Thank you for tuning in. Let's look at a schedule, shall we? So this is the, oh, okay. We got a little shadows from power lines. We can deal. This is the week that was. Spokane Geology, John Stockton's house on Tuesday evening. George Beck, Israel Russell. Yesterday morning we were talking about the valley here, Kittitas Valley, and we took a walk at the end of the program, so that was an extra long program. And here we are this morning talking about paleomagnetism. This should be interesting. Meaning, what do I have to say about paleomagnetism? We will let the Great Spirit move us this morning, and hope for the best. So is there a next week? Yes, there is a next week, but I've just decided we're doing this 2 more weeks. 2 more weeks. So, dramatic reveal for this coming week. I'm not going to see you tomorrow. Monday, we don't see each other. Tuesday, we will be talking about Whoa. Is that bleached out? Landslides in Washington primarily. Wednesday, 6 p.m., Thomas Simons. I'm going to go with Simons until proven otherwise. You know, these live streams have been invigorating in many ways, and one of the invigorating things is having all these emails pour in with all sorts of tips and leads and links and things like that. So it's overwhelming, the number of emails that I'm receiving, but it's so terrific. So I announced last week when discussing, I didn't announce it actually, I was just thinking out loud, like I was talking about Israel Russell and then George Otis Beck, and then somebody asked about the original discovery of Lake Lewis here in southern Washington, and I mentioned I think this guy Thomas Simons was the first to come up with the idea, knew nothing about him. Well, things are poured in. Here's what you can do to put a Thomas Simons lecture together. Mid-1800s, coming down the Columbia, military, Wheeler Party, I have no idea. So that'll be a fun one. I'm looking forward to putting that together. Decided that Thursday, unconventional episode, we're gonna go to school. I'm gonna show you my building, things outside of my building. I'll hang out in my office for a while, talk about being a student and a faculty member at CWU. So that'll be a weird one. No prep required. And then Saturday morning, giant current ripples. And a week from this morning, a place called Yellowstone National Park. So, this is the upcoming week. Hope that you enjoy it. Are we doing okay streaming wise? Always a delay in the comments. We have a bit of a breeze. You're in Boxy McBox. You might have a little bit of wind whipping. 3x3, what? Yeah, it's pretty breezy here. 20 mile an hour-ish winds, sustained, but it's a nice sunny morning. I thought, what the heck? Okay, everybody's bored just saying 5x5, so they're 2x4, 100 by 100. Okay. A lot of rocks for paperweights here this morning. I have one thank you this morning. A nice little packet here from Happy Valley, Oregon. That sounds like a wonderful place to be. Happy Valley, Oregon, from Lawrence. So what was in the pouch here from Lawrence? Oh, wait. I'll read you his note. It's short. Dear Dr. Nick Zentner, here are some pendants for your guests. Use as you see fit. No need to mention where they came from. I work with indigenous peoples all over the world and others who like them in their natural energy state, as well as those of us who appreciate the minerals and gems. I never labeled them, since I know who they are going to. Hope these orphan pieces find good homes. Lawrence, I appreciate the online classes. So thank you very much, Lawrence. Liz has already, so Lawrence had all these pieces and then he put in some string as well. So Liz has already picked her favorite. I hope that's okay, Lawrence. So she's wearing hers this morning as she's reading inside. And I picked this piece. And gems, jade, pendants, rings, more. Vibrational energies in gems, chakra development. So I could use a little of that, Lawrence. So thank you very much. And I can share some of the other, what did he say, kind of random pieces or something? And so we've got some, well, maybe I'll just do it this way. Got some quartz crystals and other pieces. So I will, Lawrence, I will make sure that the guests that we've had so far, Susan and Bree and Walter and Randy, and who am I forgetting? Andrew, I'll make sure that they get a chance to pick out one of these pieces here. And we may have a guest this coming week as well. So much appreciated. Thank you, Lawrence, very much. I got 2 minutes according to my watch, a couple more hellos, and then I need to start thinking about things. Good morning, Carlson family. England, another UK, Switzerland, homie. Liberty Gold guest. Oh, Rob, correct, yes. I'll make sure Rob gets one. Tacoma, good morning. Eastern Idaho, nice. Mexico, Ray, good morning. Germany, hello, Thomas. Edmonton, Alberta. Wales. You know, way back when we first did one of these morning sessions in the weekend and I saw these international places checking in, boy, it got me. It just got me. It still kind of gets me. Nobody needs to see anybody sobbing on camera. I almost did that with the Israel Russell show. Whew, I think we're all a little bit extra emotional these days. I can't speak for you, but I can speak for myself. Samuli in Finland. Brogan, Bubble Boy, good morning. God, I found this YouTube of this cover of a Todd Rundgren song, and I just, so good. That was 4:30 this morning. I've listened to it about 72 times since. As I've been preparing for, what are we doing? Oh, God. Seriously? Okay. 9 o'clock already. Give me 2 extra minutes, would you? Thanks for tuning in. We will begin in 2 minutes. Well, a pleasant good morning to you all. Thank you for joining us here. My name is Nick Zentner. I teach at the college in town. I teach primarily Geology 101 and have been doing that every quarter since 1987. And I teach some other courses, a field course and some other things. And I do some general programs for the public as well. And I've been doing these live streams, 5 of them a week since St. Patrick's Day. And we have a couple more weeks of this before we start traveling and doing some other things. So we're in the home stretch of this series, and I wanted to tackle this topic the best that I can. And the first thing to say, it's not a disclaimer, it's not meant to be a disclaimer. I don't teach paleomagnetism. Even in 101, I've kind of avoided it because it's a difficult topic. It's a hard, difficult to comprehend set of ideas. And you can see the plan here this morning is to talk about portions of the paleomagnetic discussion that I do feel comfortable, at least to a certain degree, discussing. So we'll talk about magnetic north and how magnetic north has been changing, and that might be news to you right off the bat. I'll do a little bit on the magnetic field, but I am no physicist, I'm no chemist, I'm no mathematician, and you need that. You truly need that. And by the way, down below right now in the show description, there's just a little paragraph. I added a link already. And it's a link that was sent to me by, I think, Kathy in Australia via Nancy Holtquist in Ellensburg here. But it's a textbook. It's an online textbook that's available to anyone for free, and it's called Paleomagnetism. And if you feel like you have a good handle on paleomag and you know all the ins and outs of paleomag and you tell all your friends and lovers about paleomagnetism and all of its power, you may very well have a handle on it to the depths. But just to check that you really know thoroughly paleomagnetism, I encourage you to read Bob Butler's textbook. The link down below is for Butler's textbook. So hang on just a second, Patrick. I printed out a couple pages because I was like, I love Bob Butler. I'm a big fan. He's University of Arizona, whole career in paleomagnetic research, field geologist, etc. He wrote this book in the early 90s, and I'm sitting down and I'm snuggling up and I'm like, oh God. I mean, I took calculus, but that was 1984. Haven't really done much calculus since, Bob. So and he's not trying to blow you away. He's doing his best to actually make this work for you. But if you have the abilities mathematically, physics, etc., even chemistry, when we start talking about paleomagnetism with minerals and locking in grains, I encourage you. So here's the title in case you don't see the link somehow. That's the title of the book by Robert Butler, copyright 1992. And at some point he got the copyright back and said, I want this free and available to anyone who wants to learn. And just to give you a sense of Bob here real quick, so he's got a little preamble for each of his chapters. And I like what he writes here for chapter 3, which is the origins of natural remnant magnetism. Basically, here's Bob. Of all the chapters in this book, this is the big enchilada, the one you cannot skip. The physical processes leading to acquisition of natural remnant magnetism are presented here. Perhaps the most fundamental and fascinating aspect of paleomagnetism concerns the processes by which the geomagnetic field can be recorded at the time of rock formation and then retained over geologic time. We, and he means Bob and Merle Beck, who helped him tremendously with this text long ago, 30 years ago? We want to remove any hint of magic from this aspect of paleomagnetism, preferably without removing the reader's natural astonishment that these processes actually work. Only the basic physical principles of each type of natural remnant magnetism are discussed. So he has, coverage of each of these remnant magnetism issues, none of which I understand very well because I'm a chicken. I don't know the background at all. And Merle Beck, who again we're going to talk about briefly here this morning, and hopefully Merle's watching this morning. Hi, Merle. I got a little help from Merle on an exotic terrain lecture I did a few years ago involving Baja, BC, and then Merle sent me a couple emails afterwards, and one of them I actually found, and this is Merle talking to me after seeing my just basic exotic terrains lecture. He says, Nick, sort of a quibble. This is Merle talking. When you talk about igneous rocks acquiring a magnetic direction, you seem to imply that the grains themselves physically align with the magnetic field. Actually, those ferromagnetic grains are frozen in place long before they are cool enough to become magnetic, 500 degrees or so, often less. What happens is that they align their magnetic moments with the field by a complicated process called thermoresonance acquisition. I doubt if even you could boil that down for a general audience. Thanks for the compliment. You're right. I'm not up to that. So right off the bat, I hope you get a sense that this is a difficult topic, and yet I think we can do some things. I think I have a few things I can offer you this morning that are not in those gory depths, but still have a little bit of practical application. So to start, and we'll also go down and talk about some things we've discussed on these live streams, and somehow paleomagnetism is connected to the seafloors of the world, the Columbia River basalts, the German chocolate cake, and also even the Ice Age floods. Somehow there's a connection to the Ice Age floods with paleomagnetism. Okay, so how can we start? Well, I've mentioned a number of times that I, for 20 years, taught a field geology class down in the Owens Valley of California. We would take Central kids every September. We'd usually have 3 vans, and we'd load them up with our 25 students. And we'd drive 2 full days to get down to the Owens Valley of California. We stayed at the White Mountain Research Station, and these are sophomores. These are folks who have just taken 101 or maybe one other class, and they're excited about learning how to make geologic maps and get into the program, essentially. And so one of my tasks as I was getting ready in late August for each year's group is I would take our box of Brunton compass, because each student was going to be issued a Brunton compass, and this started in 1994. And like a little mother hen, I would take my little screwdriver, and this is truly a compass, you know, we're talking about the magnetic field. Hey, by the way, I brought in a magnet. I didn't know how I was going to use it. Oh, okay. So I've got this guy, and I got these that I can barely even get apart from each other. But anyway, I said, well, I'll just use it as a prop. I was setting up this morning. Are you low enough to see this? You see my favorite little rotating globe, which rotates on itself using the magnetic field. Still magical to me, I have no idea, but I happen to have this close to the globe. Can you see that? I'm sidetracked already. It's almost like I'm stalling because I don't know what I'm talking about. Whoa! Sorry, Mom. Got it. Got it. Right between the eyes. So there is an invisible magnetic field here. There's an invisible magnetic field over there in Mexico. There's an invisible magnetic field in Finland, etc. Okay, great. So my little job was to take my little screwdriver and to tweak this compass, like I'm tuning up the compass, getting ready for the students to be field mapping down in the Owens Valley of California. Now, what am I doing with this? My job was to set the declination, to set the magnetic declination for this compass, because they were going to be using this compass not in Ellensburg, Washington, but in Bishop, California. And I'm going to try to do this so that you can actually see. I don't know if you can. Can you see? Up in here, there's a little kind of a golden spike. And now I'm twisting the screwdriver and I'm setting the magnetic declination. Don't know if you can see that or not. But anyway, my point is, without even looking things up, I just went 14.5 degrees. The magnetic declination for the Bishop, California area, 14.5 degrees east. And that's different than Ellensburg. So you're like, well, I'm lost already. I don't know what you're talking about. I've never even heard of magnetic declination, and why are you doing that with the compass? Okay, well, that's how we're going to start. All maps, whether you know it or not, have a little indication that there is a magnetic declination for that area on the map. So we all know, I think, that north is to the top of the map. That's the conventional way that we operate with maps, at least here in the northern hemisphere. And yet, true north is not the same as magnetic north. So when you're out in the field using your compass, what does your compass do? The needle in your compass points to magnetic North Pole, but that's not the same as true north. And so you make that adjustment on your compass. You basically trick your compass into thinking that you're pointing to true north because you make the adjustment. You actually come up with the declination, which you read off of the map. You make the adjustment and go, okay, I know my needle's pointing to magnetic north, but I want to plot my information on my geologic map to true north. Okay? Simple enough. Well, I taught that class for 20 years. I taught it first in 1994, then in 1995, blah, 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 all the way up to 2014, I guess it was, 2013. And every year I'd say, well, I don't know, maybe the declination's changed a little bit, but I didn't even bother to look it up. It can't be that much different. Well, I looked it up last night. Like, what's the declination now? Is it still 14.5 degrees east at Bishop, California? The answer is hell no. Sorry, Patrick. So, this is what I always used for Bishop, California, Ellensburg, Bishop, California, magnetic north in 1994 when I started teaching the classes, and the topo maps I was using were from 1994-ish in the Owens Valley, and we had that declination of 14.5 degrees to the east. Well, can you read this? The magnetic field, the magnetic North Pole, has moved hundreds of miles since I started teaching a field course in 1994. I had no idea. Maybe you knew that. I didn't know that. I didn't know there's been that much movement just in the last 25 years. So that excited me. I actually double-checked it. I thought, is this a crummy website? What's? And I went someplace else and went to some official-looking place, and they all say the same thing. So we're still just talking about magnetic north, and the fact that we'll start with Bishop. So there's that 14.5 that I always used in 1994. I looked it up today. Where'd it go? So there's been so much movement for the magnetic north that from Bishop, California, you're now setting your declination west as opposed to east. And I went back in time. I found an old map from Bishop, California, and looked at the magnetic declination from 1903. And it wasn't that much different than 1994. So there's been this crazy amount of change in the location of the magnetic North Pole pretty much in the last 25 years. Let's use Ellensburg as another example. Should I pull back here a little bit? Can you read this? So this is the magnetic declination today. Back in 1994, when I was setting the compasses to do some field work in Ellensburg. And then here's George Otis Smith's map in 1903. So my first major point, which I'm guessing many of you are aware, is that the magnetic of the field of the Earth is constantly changing. And this is, I'll go ahead and say it. I get a lot of emails from folks. Some of them are free thinkers. Some of them like to kind of have their own theories, their own ideas. I'm all for that. I'm happy to read that stuff. But it's usually kind of a, well, I know you're kind of from mainstream science, and I'm kind of from outside of mainstream science, and here's my thoughts. So, okay, there's no training, there's no math, there's no chemistry, there's no physics. It's just kind of feelings, and here's my set of ideas. Again, I'm fine with it, but magnetic field usually comes up in those kinds of discussions. Is it an accident that the magnetic field is invisible and difficult to verify by all going out to the rock and pointing to it and saying, I don't think your free thinking works because we can all see we have a field check? These invisible, inaccessible things are kind of a petri dish for free thinking to the point of removing themselves from the field evidence that we do have. And so that's part of what I'm trying to do here for you. I'm going to the laptop because I want to show you a couple of little snapshots I found this morning. I didn't even have time to go to the office and print them out. But I find them fascinating, and maybe, hopefully you will too. There's probably going to be some glare here, but we'll try anyway. Get this real big. We are going to the Cozy Fort, but I don't want to set it all up just for this. So here's how much the black dot is true north. That doesn't change, of course. Our globe is spinning around true north. But the magnetic North Pole, where the compasses are pointing, look at that change and that acceleration of the position of magnetic north since I graduated from high school in 1980. Now, I'm not here to provide answers, to even speculate. I'm just trying to share good, hard observation, good, hard data that we have. The magnetic field has changed. Now, that's since 1900. That's the last 120 years. There wasn't too much glare there. You could read that, right? Let me show you another image that is similar, but it goes back further. Now, this is doing the same thing. Where is the magnetic North Pole in the northern hemisphere from 2020, right now? This one's going back to the year 1590. So it has been moving. But again, there's 1994 when I started that course, and there's been this acceleration. I got some notes here in my pocket. That's how prepared I am. I double-checked this with two different sites. Since 1831, the magnetic North Pole has traveled 1,400 miles. And that was a relatively slow wander of the magnetic North Pole until the 1990s. And it's accelerated now to about 34 miles per year. The magnetic North Pole, 34 miles per year. Much faster than any time in the last 4 centuries. Okay, so that's declination. That's talking about measuring at your location where you're doing your mapping, what is the difference between true north and magnetic north. And this declination is different based on where you are on the planet, but it's also different depending on which decade you're talking about. It's in movement, it's in flux. Probably a bad choice. And we're not to the next segment of our session where I'm going to be using words that I don't even really understand. Our youngest son, Jack, is a physics major, and he should give this. I barely remember any physics. But I would like to comment on some basics that at least I understand. Apple from Wenatchee, specifically from Stemilt, a Honeycrisp apple. That's where Randy spent his youth, Randy Lewis, in the Stemilt area of Wenatchee. Okay, good. So we all know that the earth is like an apple, and the thickness of the crust of the earth is analogous to the thickness of the skin of this apple, and that we do have a core of the apple just like we have a core of Mother Earth. And I think we all know there's a solid inner core and a liquid outer core. This has been proven time and time again by studying seismic waves traveling through the earth, etc. So there's still major mysteries that remain, but it seems very likely that our magnetic field is connected to action within the liquid outer core of planet Earth. I found this from a field trip that I led a couple of years ago. And so far, all I want you to notice is that this poorly drawn apple, here's the invisible magnetic lines that are running through our planet. The planet's like a huge giant magnet. And I want you to notice that the intersection of the magnetic field lines with a particular latitude varies in angle. So this is inclination. So inclination is different than declination. Declination, remember, is just looking at a map and figuring out how many degrees you are in the horizontal plane away from true north. Magnetic north, true north. What's the angle between those in a horizontal plane? But in a vertical plane, inclination is talking about if I'm studying the magnetic field lines, invisible, coming into the Earth at the North Pole, the inclination is going to be 90 degrees. Those magnetic field lines are going to be coming straight into the Earth from overhead. And if I am at the, what's going on here? Why am I cut off? I'm cut off, but I think you can imagine that if we're at the equator, the invisible magnetic field lines are going to be horizontal. They're not going to intersect the surface at all. But again, if we're at a certain latitude, someplace between the equator and the pole, we're going to have these invisible magnetic field lines intersecting the surface of the Earth at a particular angle. And that's going to be important now in just a second. So if we use this hokey analogy then, so we have invisible magnetic field lines parallel to the Earth's surface at the equator, straight down into planet Earth at the north and at the South Pole, and then let's say you're 47 degrees north latitude, which is where Ellensburg is located, we're going to have these magnetic field lines coming in at a particular angle, not vertical, not horizontal, a particular angle based on the latitude. Well, that whole concept is what sets us up for a discussion of Merle Beck and his study of Mount Stewart. So I've shared this with you a number of times. This is a beautiful sample, a nice big sample that I usually have outside of my office door. Somebody cut it with a rock saw. And in this granodiorite from Mount Stewart, which is 93 million years old, this is the mountain range just to the north of Ellensburg, beautiful mountain range. Back in the late 1960s, Merle Beck from Western Washington University took careful samples of this granodiorite from Mount Stewart, knew the age of the granodiorite was 93 million years old, and actually measured the magnetic orientation, measured the orientation of a mineral called magnetite. So there are certain minerals that can cool. Let me show you a diagram. You notice when I close my eyes, I'm either confused, I can't remember, or I'm thinking, oh boy, this is going to be tough. Come on, boy. So this is an igneous rock with minerals that are randomly arranged to the naked eye. And generally they are randomly arranged. But at a very tiny level, there are some minerals called magnetite that are not random. You just shook because I set this huge sample on the ladder. If we think of our invisible magnetic field lines in a place where we have a molten magma chamber, it doesn't have to be underneath the volcano or not, it doesn't matter. We've just got a big blob of liquid hot magma underground, and we're going to slowly cool that magma, and when all is said and done, the magnetite minerals are going to freeze in position within that solid igneous rock. Because they're magnetic, they're going to line up with the invisible magnetic field lines. And what Merle and his colleagues have done for a whole career, 50 years plus, is visit rocks that were once molten and have solidified. They figure out the inclination of the magnetite grains. They note the latitude where they are currently. They note the age of the rock, and a crucial point here is that once we lock these magnetite grains into a granite, let's just say granite, okay? Into a granite, the magnetic field can change as much as it wants. Since this rock formation, it's not going to affect these grains. So when we're liquid, those magnetic, think of them as iron particles if you like. You've maybe seen a demo of magnetic iron filings on a piece of paper getting all parallel to the bar magnet. You know, I probably should have done that here. Didn't think of it till right now. But the point is that dancing, that alignment, that freedom of those magnetic grains is possible when everything's liquid. But when we cool it off and we solidify it, it's a time capsule. It's frozen in time. Now, a key part of this, from my point of view, is, well, how could you possibly measure that? What, are you just banging off a piece of rock off of Mount Stewart and take it back to your lab? How can you measure the inclination of those grains? And ultimately get to an idea that a piece of granite from Mexico has moved almost 2,000 miles north. Well, we're going to visit with Merle and Bernihausen at Western Washington in a very short Nick on the Rocks clip that I'm going to share with you in the Cozy Fort. But if I can find the diagram, I have at least a general sketch from Bob Butler's book. Oh, come on now. Come on. Where is it? Hang on, Patrick. Hang on, Patrick. Here we go. So there's a certain kind of drill. And if you're a field person and you've been out to many rock outcrops, every once in a while you'll stop at a spot and you're like, okay, I wonder if anybody's ever been here looking at this rock outcrop before. And then you see this big hole that's been drilled into the basalt or granite or something. Oh, okay, Paleomag person was here. They truly drilled into the rock. You'll see some samples in the video clip. They're little cylinders of rock. But before they pull the cylinder out of the outcrop, with their special drill, kind of a hollow core drill, they use a Brenton compass and they truly measure the orientation, very carefully measure the orientation. So something along this line. So they can drill into, let's say it's Mount Stewart, they can drill into the granodiorite at Mount Stewart. Maybe they're in the Icicle Creek drainage, you know, they're up from Leavenworth a few miles. On the right, they pull over, they find some good fresh looking granite. They drill into that granite of Mount Stewart, and before they pull the core of granite out of the mountain, they take careful notes of these orientations and then do some stuff in a lab, which I don't understand, to actually figure out. I'm not even going to comment on what I think they do. You'll see that clip. I'm not going to go through Baja, BC again for this lecture because we've had a whole session on Baja, BC. But the only point is, Merle Beck first published in 1970 on the paleomagnetism that I just tried to describe in the granite of Mount Stewart. And he said this granite did not cool. This granite did not go from liquid to solid in Washington. This granite, 93 million years ago, went from liquid to solid in what is now Mexico. It was at 23 degrees north latitude instead of the 48 degrees north that it's at now. And I can prove it by the alignment of the magnetite grains in this granite. And everybody in chorus said, baloney, partly because very few people have the background to understand paleomagnetics. Even in grad school in the mid-1980s, we were reading these paleomagnetic papers when I was at Idaho State University, and even the professors are saying, well, let's read some of these papers from these paleomagicians. So it's not an accident. Bob Butler said, we want to remove some of this magic that people seem to think that we're up to. It's careful science. And the reason that I am very excited to always tell the story of Baja, BC, number one, it's a local landmark. Number two, there are many different kinds of field evidence now that back up Merle Beck's original conclusion in 1970, that we truly do have thousands of miles of movement over the course of a 25 million year span. Topic for another day. Okay. I'm not even to the topic that many of you want to talk about. It's already 9:30. This will be a long one. Whatever. There's lots to talk about. Mostly I'm going to have the animations do the heavy lifting for me here. But I do want to comment on the basics of paleomagnetic reversals. If it hasn't dawned on you yet, paleomagnetism is talking about how the magnetic field of the Earth has been changing through geologic time. Not just the fact that the magnetic North Pole has been wandering. In fact, I think Butler had... Why not? Butler had a diagram in his text, which you can get to in the link below, that went back hundreds of millions of years. Oh, is it worth it? Yep. No, not hundreds of millions of years. In the past 2,000 years. So instead of looking at the magnetic north position in the last 50 years, in the last 300 years, Butler says, let's go back 2,000 years. So those are dates AD. 1400 AD, 1700 AD. And you're like, well, how do they know that? It's like, well, I don't really know. You'll have to read the text. I can guess, but I don't want to get into that right now. So, have you heard about this concept called magnetic polarity reversals? Okay, let's say you haven't heard about it at all. The idea is, right now, in 2020, and you can do the same thing in your apartment right now, you're still locked down, you can take out your compass, and the white tip of the compass is going to point to magnetic north. So if I hold the compass perfectly horizontal, it's free to move, and this compass needle is going to line itself with the magnetic field, and the white tip is going to point to magnetic north. Now, there have been times in our history that the white tip would be pointing 180 degrees away from this. It will be pointing to the magnetic South Pole instead of the magnetic North Pole. Many, dozens and dozens of times. That there were times you could live on this planet where the white tip of this needle would point to the magnetic South Pole and not the magnetic North Pole. So we have names for this. If the white tip is pointing magnetic north, that's called normal polarity time. Normal. Like, we're normal right now. It's normal for us to experience this. But there's another time called reversed polarity, where the white tip is pointing towards the magnetic south pole. So these magnetic fields have been flipping through time. Let's cut right to the chase. We don't know why these reversals happen. And if you're commenting right now, yes we do, here's the reason. I don't believe you. You talk to the most sophisticated science people, they don't know why these reversals happen. Everybody assumes it's got something to do with fluctuations within the outer core, the liquid outer core of the planet. But it's difficult to explain the reversals. And a big part of that is there's no pattern. There's no regular pattern for these flips. So it's normal polarity right now. I just showed you, right? The white tip is pointing to the magnetic North Pole. Are you aware of the most recent flip? How many years ago do we have to go back in geologic time to get to the most recent flip? I'm going to wait. I know I'm running long, but I don't care. 350,000? More recent than that. Every 22,000. I disagree. Okay, so nobody really has the answer. Interesting. Wow, I'm actually kind of surprised. I still don't see the answer. Okay, so here's the number. And I'm really surprised. So I don't know. I mean, you guys are geology fans. Wow, really? Okay. 780,000. The last time, the most recent time, Mother Earth has flipped magnetic fields from normal to reverse, backwards. From reverse to normal is 780,000 years ago. Before I show you this chart, let me make sure, because I'm totally blown. I'm usually not that surprised, but I'm really surprised at this. I appreciate you chiming in, and we don't, we're not embarrassed to just guess, but wow, okay. So he holds the poster between his knees, and here's normal polarity, where the white tip of my compass needle is pointing to magnetic north, just like we were discussing. And that has been normal polarity consistently since 780,000 years ago. But if we step just a little bit older than 780,000 years ago, and that's almost a million years ago, right? If we go just a little bit older, Butler boy, than 780,000 years ago, and now we are older, just a little bit older than 780,000 years ago, now we have a reversed polarity. And the white tip of my compass needle is pointing to the south, magnetic south pole, as opposed to the magnetic north pole. This is known as reversed polarity time. Okay. So maybe of all the things we're doing this morning, especially since we were all over the place with our guests, I hope that this chart, which is conventional, it's not controversial at all in geology, I hope this chart will have some meaning to you. And for all I know, there's mutiny right now. I have no idea. So I stole this off the wall of our first floor in our geology department. It's oh my God, it's so big I can't even get it on the screen. I got nothing to hold this up. But this is the entire geologic time scale. Today is here, going all the way back to 4.6 billion years ago. So this is the Precambrian over here, and the Paleozoic era, and the Mesozoic era, and the Cenozoic era, with all the names of the periods and the epochs and everything else. Now, why am I showing this to you? Well, I'm going to bring this in because I'm starting to get whipped around. I'm going to bring this in close to you, but can you see there's a it's like you're at the supermarket now and you've got the barcode. you're doing your self-checkout thing because you don't want to deal with anybody, you got your mask on and all that, and you go through the self-checkout and you, where's this damn barcode, you know, so you can scan it. And I always get, you know, I always need help. Like the old gentleman needs some help with his barcode. Okay. So there are no barcodes over here. In the Paleozoic and the Precambrian, we don't know anything about magnetic field reversals. But starting this morning and going back in time, these are ages in millions of years ago. And this barcode is talking about the history of our magnetic field. And this is from rocks. This is from studying rocks. This is from studying rocks that have the ability to lock in their magnetic grains. I'll give you more on that in a second. So the black that you're looking at are normal polarity times, when your compass needle, the white tip of your compass needle, is pointing to magnetic north. Black is magnetic north, normal time. White is conventional way to show reversed polarity, meaning if you're living during one of these white bands, your compass needle points to the magnetic south pole. So let me just run this through you. This is such an unwieldy map, or a poster. Yes, the robin is enjoying the discussion of magnetic field. We're back now to 66 million years ago when the dinosaurs disappeared, the massive end of Cretaceous extinction. That's just look at the Cenozoic history of paleomagnetic reversals. Let's do the same thing for the Mesozoic. Why not? You know what we're doing? By studying paleomagnetism in rocks around the world, not just here in Washington, rocks around the world, in the sea floor. You see where we are? Now we're down in the Mesozoic, 70 million years ago. Black is normal polarity. Look at this. That was a big normal polarity time. So are these guesses? Hell no. Sorry, Patrick. Absolutely not. These are not guesses. These are what the rocks tell us around the world. And you're like, so there's granites around the world that tell us this? It's more than granites. I showed you this, saying that granites of a certain age can lock in their grains at a particular inclination, and we can decide whether it's normal or reverse polarity, but it's not just granites. We can have lava flows that have iron minerals in them, like basalts. And the basalts, when they go from molten to solid, will, if they have enough magnetite material within them, can record whether it's a normal or reverse polarity time. And are you aware this can also be done with sediments? Layers of silt, layers of sand. If there's iron particles in that sediment, again, the grains are free and able to align themselves to the magnetic field, and then they can get locked in the sedimentary rock and not allowed to continue to move if there's been a polarity shift since that time, or a polarity change since that time. So we're getting close to the cozy fort because I need a little bit of help with some animations and some visuals to make sure this is going down well. But my instinct as a teacher is to like open it up to the room now and say, what is not working for you here? Why were we so confused about 780,000 years ago? But I guess I don't have that ability in real time to do that with you all. So I think I'm going to finish up my portion before we go in the cozy fort with a couple final things. When I came here to Central Washington in 1992, and I went out every morning with Bob Bentley and spent every day in September with him and his students in the Yakima Canyon and other places. And my job was to learn, because I had never lived in Washington before, to learn these different layers of the German chocolate cake, to learn these different Columbia River basalt lava flows. And they all look the same to me. They do to most people. And so Bentley finally gave me this, and I laminated it, so I had my little cheat sheet when he was trying to embarrass me in the van as we're driving down there. Classic Bob. And I'm showing you this because once we get down to the Grand Ronde lavas, which are the main phase eruptions between 16.5 and 16.1 million years ago, one of the main ways to tell the difference between individual lava flows locally here in the Grand Ronde is to look at their magnetism. Normal polarity, reversed polarity. And to this day, like when I'm out with Andrew Sadowski, the geologic mapper who's been mapping up north of town, he's like, yeah, I think I got N2 here. Oh, I mapped some R1 come through. So it's like shorthand for talking about where you are in these Grand Ronde basalt lava flows here in Central Washington. Because there's normal polarity, reverse polarity. Normal polarity, reverse polarity. N1, R1, N2, R2. That's the main way to tell the difference between these flows. So each of these basalt flows in Central Washington are molten, they're cooling, and when they cool, depends on what the polarity is, whether it's a normal or reverse polarity time to keep track of that. And that's been done around the world with basalts on the seafloor around the world. Animation time coming in just a second. My final thing before we go to the cozy fort. You know that most of our discussions of the Missoula floods and possibly Ice Age floods coming across the border from the Canadian ice sheet, most of that discussion is younger than 20,000 years ago, right? We had big Ice Age flood over Wenatchee 18,000 years ago, big breakup of the Okanagan lobe 14,000 years ago, giant current ripples at West Bar, etc. That's all younger than 20,000 years ago. But if you look carefully at Bruce Bjornstad's On the Trail of the Ice Age Floods books, or if you find some old papers by Bjornstad and others, there's growing evidence that there were some Ice Age floods older than 780,000 years ago. Have you heard about this before? Evidence of some Ice Age floods that are tens of thousands of years, hundreds of thousands of years older than the story we've been talking about generally. And the evidence for that is you go to sites that we've gone to on our old people field trips. This is Harder Road that's out south of Ritzville. And here's just off the freeway at George, there's a little gravel pit right there at George, Washington, used to be called Burke Junction. And my point is, in both of these cases, there's a layer of sediment that has been carefully studied, and this sediment has iron particles that are reversed polarity signaturized, which means we have a bunch of flood gravels that are sitting below a layer that's from a reverse polarity time. And the most recent time, planet Earth, that we've had reverse polarity is older than 780,000 years ago. So we can't say exactly what year it was that these Ice Age floods at these two locations happened, but it has to be sometime older than 780,000 years ago because of the paleomagnetic signature of the iron particles at those two locations. And there's other locations as well. Even in the Luss, another live stream now with the kitchen flower. If we go over to Washtuckna, and we're on State Route 26 driving over to a Cougar game, and we can find some ash layers in the Luss, okay, that's fine. But I don't know if we can zoom in well enough or not. But when you dig through and core through all this ice age loess, basically, these are in ages, oh, this is just depth. But here's the same thing. We've got some loess that has normal polarity, and we have some loess in the Palouse Hills, we have some loess in the Palouse Hills that's reversed polarity. So younger than 780,000 years ago, older than 780,000 years ago. So even the Ice Age floods, some of the evidence for Ice Age floods, we get paleomagnetic information from the sediment. All right, I got no idea where we are. Revolt, confusion, furious head nodding, yes? I don't know. But we're going in the cozy fort. I forgot my poles. I got to run to the front porch quick. Hang on. This is Cozy Fort by Steve. These live streams are out of control. Do you remember the first few live streams we did back in March? I'm like, okay, I'm going to talk for like 15 minutes and then we'll have some live Q&A. And now it's like I'm basically clearing my throat and it's 9:30. So we're just starting the Cozy Fort at like 10 o'clock. Redunculous. But I always feel like on Sunday, you know, I'm not going to see you again until Tuesday, so why not? I've been tasked with a whole bunch of stuff before our guests get here on Wednesday, so I'd rather do this than change the oil in the car and wash the windows. That doesn't sound like fun to me. A couple of our live streams we've had like stray strings dropping from the quilt roof. And I'm just particular enough that bothers me, so we might be okay. Until we get a big gust of wind and we all head into the street. I don't know, we might not do much live Q&A anyway, because I'm not going to have many answers. Merle might be with us, but I don't know if he can figure out how to join us. His words. Okay, let's get some help from, do you know Keith Meldal? He's an author of some wonderful geology books. And I found this, that he has a YouTube channel. And 3 minutes long. I think it's well done. This is almost kind of a review. Channel. Hold it. Hold it.
3 minutes long. I think it's well done. This is almost.
Stop it. Keith Meldal.
Hi, everyone.
We're going to talk about the Earth's magnetic field and how the reversals in the Earth's magnetic field revealed that seafloor spreading is happening. The Earth's magnetic field creates lines of invisible force that you can't see, but that your compass needle senses. And the reason your needle points north is that these field lines emerge from the south magnetic pole and wrap around and point toward the north magnetic pole. Now, we know that the Earth's magnetic field has actually reversed, flipped around, so that these arrows would all point the other direction, coming out of the north and pointing into the south pole. And these are called magnetic reversals. They happen every few million years. The Earth's magnetic field flips back and forth through time. The reason we know this is that lava flows, like this lava flow on Hawaii, when lava flows out of the Earth, it actually, there's little magnetic minerals in the lava, and they line up with the magnetic field at the time and actually preserve, like a tape recorder, the direction of the Earth's magnetic field, whichever way it was pointing, either normal or reversed. So if we go look at a whole series of lava flows, what we'll find if we sample through the lava layers into older and older layers, we'll find some layers that are oriented with a magnetic field, say like today, and other layers, older layers that are reversed, and then still older layers that are like today. So through geologic time, the Earth's magnetic field flips back and forth, and we call these magnetic polarity reversals. Now, the way that this all relates to seafloor spreading can be realized by remembering that lava is pouring out of the Earth at mid-ocean ridges. Okay, so I want you to imagine that we're going to let this ocean basin spread, and we're going to let the Earth's magnetic field flip back and forth as the ocean basin spreads. Remember that when the lava erupts and cools down, it records the direction of the magnetic field at the time, whether it's normal or reversed, backwards or forwards. So we'll start the animation here. We're going to start it at a time when the Earth's magnetic field is like today, what we call normal polarity. And as the seafloor spreads, it's all going to get polarized in the direction of the magnetic field, shown by the blue part of the ocean floor. But now we have a reversal happening, and any new lava that erupts is going to get magnetized in the opposite direction. So you can see the little compass needles here have flipped, showing us that all this new seafloor is recording the direction of the Earth's magnetic field at a time when it was reversed. Now we'll let the Earth's polarity flip again. Any new lava that forms is going to record the polarity of the Earth at that time. So what we see on the mid-ocean ridges of the world today is a series of stripes, symmetrical stripes on both sides of the ridges of seafloor rock that's magnetized in the same direction as the magnetic field today, older rock that's reversed, still older rock that's back to normal. This pattern is impossible to explain if seafloor spreading didn't actually happen and the Earth's magnetic field didn't flip back and forth. So it constitutes some of the best evidence we have that the seafloor is actually spreading.
Keith Meldal, who just retired from teaching geology at a college in San Diego area, got an email from him last night. You want to meet the guy who discovered in the 1960s that paleomagnetic signature on the seafloors? He's famous in geology world. Fred Vine. So Vine and Matthews, that was on my chalkboard. I found this old clip about an hour ago. He uses a chalkboard back in the 1960s to talk about the confirmation of seafloor spreading using paleomagnetism. And then late in this clip, he talks about the seafloor paleomagnetic reversal record off the coast of Washington. He calls it the Northeast Pacific, but it's the Juan de Fuca Ridge off the coast of Washington and Oregon. Fred.
Frederick Vine explains his discovery. A connection between those magnetic reversals and Hess's conveyor belt, which determines the speed of seafloor spreading.
Oceanic crust, the seafloor, is continuously being created at mid-ocean ridge crests, such as the crest of the mid-Atlantic ridge here in the South Atlantic. It is generated above an upwelling in the mantle and spreads laterally away from the crests, thereby separating, drifting the continents apart as though they were on a conveyor belt of upper mantle material. So one might represent this, therefore, by a simple model such as this.
Nice.
Illustrating the way in which the conveyor belt of oceanic crust and upper mantle material flows out from this central crack in the Earth's crust. Well, now in 1963, Drum Matthews and myself, then at Cambridge, added the simple rider to this, and in effect converted his conveyor belt of oceanic crust into a tape recorder. We suggested that as new crust is formed, solidifies at a ridge crest, frozen into it will be the current direction of the Earth's magnetic field. This will be subsequently moved aside as newer material comes in. And in this way, successive avenues of crust, normally and reversely magnetized, will be built up, paralleling the ridge crest and symmetrically disposed about it. And indeed, going back to the anomaly map, the very detailed contour map of Raff and Mason for this area of the Northeast Pacific, and after peering at it for some time, we could see that indeed there is a remarkable symmetry of the magnetic anomaly.
He's not flipping you off.
The crest of this so-called Juan de Fuca ridge in this area, and they do indeed reproduce all the details of the reversal timescale in remarkable detail. So to summarize this then, we drew up this new colored summary map, which emphasizes this symmetry about the ridge crests in a truly remarkable way. It's incredible to think that it had been in the literature for 4 or 5 years. In '63, it was very frustrating because I had this idea and one realized that if it was true, you know, the implications were enormous. That the ocean basins were young, ephemeral features, that all the oceanic crust, all the deep ocean basins that we see today were generated, say, within the past 200 million years of geologic time, less than 5% of the whole of geologic time.
Let's keep it going. I got the volume cranked. Those were too quiet.
The idea that our planet's continents drift around the globe, periodically glomming together.
Knock it off. Oh no, we don't want this one. Hang on, Patrick. This is 18 seconds. No sound, but another little animation showing seafloor spreading anywhere in the world. It doesn't have to be the Atlantic or the Northeast Pacific. But you can see the normal and reverse polarity bands. You want to see that again? Okay, so that's reversal business. I think it's appropriate to close that window. Right. I think we need to meet Merle. This is a 5-minute clip that we shot a few years ago. We drove up to Bellingham. I'd never met Merle before. He was one of the best guys we've ever had on camera. He just tells us immediately well-spoken and fun and interesting, especially with this very complicated topic. So this gives you a little bit more,
the mysteries of the earth.
a tiny bit more depth with the Baja BC and drilling to measure the inclination of these magnetic grains in the Stewart Range. Nick on the rocks, Mount Stewart from Mexico, question mark?
Discover the energy that drives a planet and builds mountains. Uncover buried treasure and see what makes mountains blow. Find out what shapes the top of the earth and explore the secret world below. With me, Nick, on the rocks. Mount Stewart is at the center of a fascinating mystery connected to one of the greatest discoveries in the history of science. 100 years ago, they thought the world's land masses were always where they are today. But this man, Alfred Wegener, thought otherwise. When Wegener looked at the globe, it appeared to him that parts of some continents fit into other parts of other continents. He suggested that long ago there was only one continent. He called it Pangaea. Almost everybody else thought Wegener was nuts. Wegener spent the rest of his career, another couple decades, going around the globe trying to find evidence to support this idea. And unfortunately, he died in the 1930s in Greenland on one of these expeditions collecting evidence and never did see his ideas accepted by the geology community.
general, mountain ranges rise in response to crustal compression. And the compression is coming from collisions between plates. We're lifting the rock up. And if we lift this rock up, the stuff at the top is going to be the first to get eroded away. And those core rocks in Mount Stewart are the center of an ongoing geological debate. It's not part of the Cascades, geologically. Geographically, we can lump it with the Cascades. But the rock is way too old for the Cascades story. Cascades have only been there for 40 million years, only. And the rock in Mount Stewart is 93 million years old.
A lot of evidence has accrued over the years that major chunks of the western edge of North America didn't form as part of North America. They formed out in the Pacific someplace and were transported by plate tectonics, generally from the south to the north, and then they were plastered onto the continent and then sheared up.
Mount Stewart was part of an exotic terrain that attached itself to the western edge of North America. But where did it come from? Geologists at Western Washington University believe the rocks in Mount Stewart were formed far from here. I drove over to Western to visit Merle Beck and Bernie Housen in their paleomagnetic laboratory. Merle in particular has spent more than 40 years on this topic, collecting samples from Mount Stewart itself and analyzing that rock for a paleomagnetic signature.
I got in pretty early. I'm not a founding father of paleomagnetism, but I'm close. You know, I'm an elderly nephew sort of thing. I got an NSF grant and I worked on rocks in the Cascades. And there it was, Mount Stewart. So we went up there and we drilled in about a little more than half a dozen places.
These granodiorite samples are part of their collection.
It triggered the whole controversy. And it's such a beautiful rock.
Yes, it is.
Paleomagnetically as well as aesthetically. It gives you the nicest directions you've ever seen.
But those directions came as a shock to the scientific world. If their initial results were to be believed, the rock in Mount Stewart originated more than 1,000 miles south of where it is today.
Everybody said this guy's nuts. And the problem was mainly that they didn't understand how paleomagnetism worked.
Is Merle right? Well, another group of scientists say, wait a minute, we don't buy that. Terrains move along faults, but we can't find a big one that Mount Stewart might have slid along. Merle Beck has his answers to those doubts, and the skeptics have more questions, so the controversy continues. This is a major unsolved mystery right here north of our campus with that landmark that everybody knows. How far did that thing travel? There'll be a younger crop of folks with some new techniques that will contribute to this, and we'll eventually get a bright person to find just the right key piece of evidence that will put the whole discussion to rest. All right, I got one more little clip, and it's a fun one. I don't know if you've ever seen this guy. I just discovered him this morning. 11 million views for this video. Have you heard of Brainiac 75? Down in the lower left. Brainiac 75. I think he's from Denmark. And I'll just play a little bit. This is a 10-minute clip. I'll just play a couple of minutes. But he's playing with this fluid, this magnetic fluid that apparently was engineered by NASA. And he's doing experiments by taking this fluid and putting it over a very strong magnet to kind of demonstrate the invisible magnetic field lines that are around us at all times. Feels like these videos are quiet today. I don't know why. I've got the video cranked, the volume cranked.
In this video, we'll encounter strong magnetic fields and messy stuff. Ferrofluid is attracted by a magnet, so much that it doesn't care about gravity and lifts up in these nice spikes, following the magnetic field lines. I have placed an extremely powerful 6x2-inch neodymium magnet under the table to control the ferrofluid. Not just for the visuals, but also since I don't want to drop this by accident directly onto the magnet. The cleanup would be... I would rather clean up after an exploded whale. But for your viewing experience, I'll get it as close to the uncovered magnet as I dare. If I go too close, the magnet will lift up or pull the glass tray out of my hands.
This is amazing.
Smashing the glass and, well, do not try this yourself.
God dang.
At this point, I was struggling to keep the tray level and away from the magnet. Time to chicken out. This magnet will always win a fight. What I do there is something that countless of you asked for on my previous video. Touch the spikes.
Oh man.
This is not recommended since ferrofluid is a skin irritant. I will wash my finger right after the recording to avoid a skin rash. As you can tell, the spikes are very soft and stain a lot. The fluid has already run under and around my nail.
I like this guy.
Moreover, ferrofluid is a serious eye irritant, so wear safety goggles and don't scratch your eye with the stained finger. Luckily, it isn't toxic, so I just need to clean my finger. Let's go a little deeper with gloves on. While on the subject of safety, let me mention that the liquid itself will destroy your lungs, so don't pour it into them. With common sense and basic safety gear, you can...
You might all know about that guy. I don't. I'll be watching a bunch of his stuff. That's very interesting to me. That's all I have for you. And I think we will do a little bit of, what is it? 10:15. I don't know, 10 minutes or something. I can try to answer a couple things. But you pretty much have heard all I care to know or care to discuss about paleomagnetism at the moment, but we'll try it anyway. I'm curious what you've got to say. And because I don't, many of these topics I already, I've got so much experience teaching, I kind of know what people are going to ask, and it's just a really known thing. But now, I really don't know where you are. Was that over your head? Under your head? Cozy Fort by Steve. All right. If you're new to us, we ask questions with an uppercase, kind of a caps lock deal. And I scroll around and try to grab as many questions as I can. Eric, do great earthquakes affect the magnetic field? How much has the magnetic South Pole moved? I know of no connection between seismicity and the magnetic field, and I'm guessing that the magnetic South Pole, we could find plots of that wander as well, like I was showing with the North Pole. However, we have to go back earlier than 780,000 years ago to have that be the dominant pole. Bob, how do we discount the sun's influence on the angle of the Earth's magnetic field? The sun's influence. I don't know why the sun would have an influence on that, Bob. I'm not sure I'm getting your question. A lot of these are going to be half-baked answers. You already know that. How long does the reversal take? I tried my best to read up last night on that. And the most conventional estimate I've seen is over the course of thousands of years. So from what I've seen and read, and you can Google just as well as I can, probably better, if you hear somebody talking about magnetic field like 780,000 years ago, how quickly did that thing switch from reverse to normal? If you hear somebody saying it takes 50 years or 100 years, that seems extreme. That's a minority opinion. But it's very difficult to prove how long it takes. And of course, you just do popular searches, and there's discussion of we're in the middle of a reversal right now and, doomsday, whatever, civilization will end. Let's just stick to what we know, which is the geologic history of how many reversals, and to give any kind of number about even one of the videos I showed, they said every 2 million years or every 4 million or whatever they said. It's way more variable than that, as you just saw. In fact, I'll show you a couple more screen grabs from Butler's, from Bob Butler's text, which again is free and available to everybody at the link right below. So here's Bob talking about some geologic formations in Pakistan and normal and reverse polarity signatures of different portions of those formations, and then taking that barcode and matching it with basically a confirmation using some absolute age dates. But what I really wanted to show you is that Bob has a lot of these barcodes. Here's just looking at a very specific look at magnetic reversals in the last 5 million years. We'll start at the top. So there's our most recent, what does he have? 0.73. I don't know why he has that. That's interesting. Instead of 780,000 years ago, he has the last flip at 730,000 years ago. You might know the answer. I don't. But here's going back 1 million, 2 million, 3 million, 4 million, 5 million. This is from basalts, this is from granites, this is from sedimentary packages, all confirming this flipping history. This flipping history. I thought, Dead Crow says, I thought you said they can't tell if paleomagnetic locating is north or south latitude. I did say that. So I don't think I said that here, but I said that in another program. The Merle Becks of the world can measure carefully with the drilling and the Brenton and everything. They can measure the inclination, but they can't for sure from that measurement say, are you 23 degrees north or south of the equator? Or 53 degrees north or south of the equator? It's just an inclination. You don't have a sense of that. So you need to use other contextual evidence from the rocks surrounding the problem to back up whether you're in the northern or the southern hemisphere. Thank you. Sue, does Santa live at the true north or magnetic north, so moves often? Good question. I'm going to go with true north. Drew, is a reversal a violent event? I don't imagine it would be. If the conventional answer, Drew, is it takes, let's say, 1,000 years to completely change from a normal to a reverse, then it's hard for me to imagine it being a violent event. Automatic scroll. 2 months later, I still haven't figured that out. The Jackson Winfrey Project asks, would a reversal trigger a Cascade volcano eruption? This is all a common speculation. Earthquakes cause a flip. Does a flip cause a volcanic eruption? Does a flip cause an earthquake? Just off the top of my head, all I can say is I know of no increase in seismic or volcanic activity 780,000 years ago when we did the last flip, or any of these switches from black to white. I don't think if there's been a kind of a regional connection with geologic hazards and these flips, you'd think we would have stumbled onto that by now. I guess it's possible, but I don't know of any evidence for that. Bubba Bong, if they know about the band of reversals, when is the next one due? Well, we do know the history of the reversals from all these bar scales. What do we call them? Barcodes. Here's another one, just going from 100, from Butler's text, from 110 million years ago to 100 and whatever million years ago. So I don't know how you can say anything meaningful about when the next reversal will happen when we've had this kind of variability in our geologic past. So to end, look at this. Here's the last 115 million years of time. In 2 columns. So I don't see how anybody can say when the next flip is happening. Can you? Now, we started with a kind of acceleration of the magnetic north movement up to 35 miles per year. Even that, what does that mean? Does that mean we're about ready to do some flip? I don't think you can say that. So your instincts are right on the mark, and you read popular articles and we're overdue or we're due. That comes up all the time. That's just humans wanting to make a pattern out of something that doesn't appear to have a pattern. Vicky, do sunspots or solar storms affect the pole movement? I don't know. We're into astronomy now and physics. I don't know. Does the North magnetic pole affect navigation? I don't know that either. I don't know about navigation. I'm sorry. M. Smith, are there rocks that solidified in the middle of a reversal and have no polarization? I think the answer is yes. I don't know about the no polarization thing, but there have been some lava flows in particular that I know about that apparently erupted during a transition time. Where is that? Well, I don't know what they're doing here. Maybe you can figure it out. We're back to our geologic time scale, and the barcode is black, white, black, white, black, white, black, white. But back in the Jurassic, they have gray. I don't know what the gray means. Is that a transitional time that's prolonged? But a more direct answer to your question, I can't find the Bentley Strat column, but do you remember the Ginkgo lava flow? That's the one that had the petrified wood and the pillows at the base. Bentley, at least, I don't think he published it, but he seems to think that the Ginkgo flow erupted during a transition time. And I don't know what those magnetic grains look like, if they're just random or what. Thank you for the question. Robert, do you think that your globe will turn backwards in the next reversal? I don't know. Again, this is from Mova Globes, M-O-V-A. My mother bought this for me as a Christmas present. We saw this in somebody's office at like an ag extension office when we were dealing with our issues last summer. Is it going to move now? I don't know how the magnetic field of the Earth is causing this guy. Is it spinning? What happened? Oh my God, we're in the middle of a reversal right now. Yeah, it's spinning. So I can't even answer a basic question like that. You may be kind of teasing, but I mean, I got deep into the woods last night. I was basically half awake, but where the physicist is talking about a right-hand rule and some kind of cells of rotation within the liquid outer core, way over my head. Jim, 780,000 years ago, any relationship to Yellowstone? I don't think so. I think the most recent supervolcanic explosion in Yellowstone is 640,000 years ago. I think the Long Valley caldera last exploded 760,000 years ago. 20,000 years younger than the last reversal. I see what you guys want, and you're kind of naturally curious about. As far as I can tell, no connection between magnetic reversals and geologic phenomenon. I'd love to be proven incorrect by somebody, but I haven't seen any of that. Valerie, no, there's no pattern to the reversals. I was trying to show you all those black and white bands there. What a reversal, so you're all asking the same thing. Tried to answer it the best I can. Mr. Joey Lauren, does the it's Gavin, age 10. Does the movement of old granite great distances, like Mount Stewart, make it harder to accurately read how the magnetite was aligned? I haven't done those measurements myself, Gavin, but you got a taste from visiting Merle Beck in his lab that they are very careful with their measurements, and regardless of the rock being 1 million years old or 93 million years old or 127 million years old, as I understand it, the alignment of those magnetic grains are the same to deal with. So I don't think the antiquity of the rock is a problem. And now it makes me wonder why we haven't gone back more than 1 billion years with our magnetic reversal records. And I guess I'm thinking out loud. Most of our magnetic reversal history is from the sea floors going back to 200 million years ago. So it's hard to find ample igneous rocks that show enough reversal information to give us a good feeling for the flip frequency once we get older than the oldest ocean floors of the world. Paul, how might polarity reversals affect changes in global climate? I don't know. Just with popular articles last night, I saw a couple, I'll let you decide what you want to think, that are suggesting that global climate change is somehow affecting the accelerated wander of the magnetic North Pole. At first thought, I don't see how there's a connection there, but maybe it's obvious to you. Ian, is the northern declination equal at all times to the southern declination? In the South Pole, you mean? I don't know, I haven't given that any thought. Not sure. Good question. It's very interesting to me. Almost all these questions are tying this invisible magnetic field flip to eruptions and earthquakes and violence and other kind of tangible geologic phenomenon. I didn't anticipate that. So if I do more presenting on this, I'll be thinking more carefully about that, ways to kind of remove that part of it, unless there's a clear reason to make those connections. How about a few more and we're done? It's 10:30 already, good Lord. We're going to do 2 or 3 more. Robin. Sherry, have they used rocks on the other side of the planet to confirm ages of reversals here? Yes, this is a global thing. That's one of the beautiful things about much of this, that it doesn't matter what country you're in, what hemisphere you're in, what language you're speaking. These rocks of a certain age, these paleomagnetic measurements, it's a global phenomenon. Isn't that refreshing that we're all on the same planet, getting the same data? Colin, what if the rock was tilted in its natural traveling? Yes, that continues to be an argument for many who are not fans of Baja BC. They see folding, faulting, warping, tilting, as you say, of bedrock units as profoundly screwing up these measurements that Merle and colleagues are taking. And it makes sense, it's a reasonable argument. But then you come back with guys like Merle, and I'm paraphrasing now because I don't really know, but they say we've taken that all into account. We know the structural relationships of these rocks. Even if it's a granite, we know how much the bedrock in central Washington has been rotated, let's say, away from horizontal. But it is a criticism, as I understand it, from many field geologists who say your inclination measurements are baloney because there's been so much structural geology happening in tens of millions of years of time. But if you keep doing this, as Merle has and others, going to the Sierras, going to craters of the moon, going to many places with different kinds of rocks in different countries, and they're all agreeing with this main story of moving large sections of crust north. Craters of the moon was a joke. That's too young for this. But the point is, there's checks and double checks and field checks. It's not work done in a vacuum. One more. Scrolling back. What temperature does the magnetism, I guess, direction get locked in, asks Jane. I read that email from Merle quickly. I think he said something like 500 degrees or less. That's kind of meaningless to me, but I guess that's the best answer I have for you. 500 degrees or less. So there's chemistry again. Certain minerals crystallizing at certain temperatures. It's impressive. A look at the schedule for next week and a toast to you. I really do appreciate you joining us. Before I walked out here, Liz was sitting in her chair reading quietly, and I said, "Oh, this is not going to feel good." Because I'm out of my comfort zone here. So this could have been a total train wreck. Maybe it went okay. Hopefully there's a couple new thoughts for you at least. Part of what we try to do with these, and we, I mean me, trying to open a door for you to get introduced to a new set of ideas if you've never thought about paleomagnetism before. Next week, landslides on Tuesday night at 6 p.m. Thomas Simons, I know nothing, I will learn. I'm looking forward, as always, to reading about these guys who lived long ago. But he was an explorer, a mapper, a surveyor in the mid-1800s. Apparently the first guy to think and discover the idea of Lake Lewis, an Ice Age lake. I'm going to be broadcasting from the campus of Central Washington University and our geology building, both outside and inside of the building, on Thursday. Giant current ripples. If the weather cooperates, I think we might broadcast from some giant current ripples. If not, I'll do it from home. And then I think it's about time to talk about Yellowstone, almost like this one, where what do we actually know? What are the facts? What's the field evidence that we all know in geology from Yellowstone? And can we please get off of these ridiculous articles that happen every other month, every other week, about the end of civilization coming very soon? Make sure you click this article so you can read about the latest. It's all just a trick. So we'll talk about that. You know what? I'm still thinking about this clip. So I'm going to do a toast to you, and then I'm going to finish with you without the cozy fort, but I'm going to play a portion of this clip. And it's a cover, so I shouldn't get into copyright trouble. I don't know. They are so good. A toast to you and your health, your physical health and your mental health. Best wishes to everyone in your family and in your friend circle and in your community and people outside of your community. I didn't know Todd Rundgren wrote this song, and I've been a fan of his for a long time. And these guys in Atlanta or something, this singer is, I can't believe it. I'm gonna play just a portion of this to finish the episode.
Love is the answer. Let it shine. Shine out that song. Set us free. Love is the answer. Tell me, are we alive or just a dying planet? What are the chances? Ask the men in your heart for the answer. And when you feel afraid, when you've lost your way, when you're all alone, when you're far from home, when you're down and out, oh, your hopes run out. When you need a friend, when you need the end, we got to love, we got to love one another.
Love you. Goodbye.